Today we're talking about different ways of communicating enthalpy so that we can describe and evaluate information as appropriate to different problems and different scenarios that we're presented with. Our success criteria is being able to describe enthalpy in terms of total enthalpy, delta H, molar enthalpy, delta HM, as part of a chemical reaction and as a graph. So enthalpy change can be communicated in 4 different ways. 3 of these ways are empirical, which means they are expressed in terms of numbers and measurements, while one of them can be empirical but is mostly theoretical, explaining the concept. Our first empirical method is to describe delta H. Delta H represents the overall enthalpy change of an entire reaction. It's of the entire reaction, so it's not actually specific to any given chemical within the reaction. The amount of delta H will also change as you change the amount of the different chemicals involved. So if you have the reaction of methane combustion, the enthalpy of that is negative 802.1/2 of a kilojoule. But if you double the amount of methane and oxygen, so twice as much reaction takes place, you also double the delta H up to 1,605 kilojoules. So delta H always gets measured in kilojoules, and we have to be really careful with it because it refers to the entire reaction. It actually refers to a specific amount as well. Like in this reaction, the first line is saying if there's 1 mole of methane and 2 moles of oxygen. Second line is 2 moles of methane and 4 moles of oxygen. Last one's 5 and 10 moles. But you could also use that to describe a certain number of grams. So you have to read the context of delta H very carefully. Sometimes it's amount of a balanced chemical reaction. Other times it's a specific mass or specific moles or specific volume and concentration of chemicals involved. We can contrast that with our second empirical method, which is molar enthalpy. Molar enthalpy I write as delta HM. Some textbooks write it as delta RH. It's not a big deal which one you use. They're both the same thing. Molar enthalpy is measured in kilojoules per mole. And the molar enthalpy expresses the amount of kilojoules being lost or gained by the reaction relative to the amount of chemical that's present. So this number does not change as you increase or decrease the amount of chemical involved because this is a rate. It's kilojoules per mole, and that ratio of kilojoules per mole doesn't change if you have 5 grams or 50 kilograms. Because this is for a specific chemical as well, we have to specify which chemical it is we're talking about for molar enthalpy. So here I can talk about the molar enthalpy of methane or the molar enthalpy of oxygen, but there's no such thing as a generalized molar enthalpy. And of course as well, just like the last one, this is for a specific chemical, the molar enthalpy or for a specific chemical reaction. The molar enthalpy of oxygen is not constant. It varies depending on the reaction you're talking about. So just make sure you remember it's specific for a specific reaction and a specific chemical within that reaction. Our third empirical method is enthalpy as an equation. In enthalpy as an equation, we're taking delta H and we are actually putting it into the reaction as a term, as if it were a product or a reactant. If the reaction is endothermic, it's absorbing energy, we treat enthalpy as a product. Delta H will be positive in these cases, so we put the enthalpy on the left-hand side because it's going in. It is a reactant as part of the reaction. If the reaction is exothermic, delta H will instead be negative. But when we write it as part of the equation, we still use a positive sign. And that's because we don't write it on the left-hand side with the reactants, we write it on the right-hand side with the products. The positive or negative when you're dealing with enthalpy is really saying, is energy being gained or lost? Not that you're adding or subtracting. We do addition and subtraction with them, but that's not what it really means. If there's a negative sign, it means that energy is a product of this reaction, or at least you're giving energy to the environment. It's being released by the reaction. So we write it alongside the other products. And we do that with a positive sign because the positive sign in chemistry isn't a plus, it's an and. So we'd be saying the reaction of methane and oxygen creates carbon dioxide and water vapor and 802.5 kilojoules of energy. Our final method of expressing enthalpy is our theoretical way of explaining it. This is a chemical energy diagram. Now, chemical energy diagrams can be quantitative. They can be empirical. However, what we're more focused on these diagrams is really understanding what's going on. And the reason that we're focused on that is because this helps us to visualize what's going on. You'll see that there's very few numbers on these two graphs, which is kind of odd for graphs because we usually like to quantify graphs and use them as math. But here we're not trying to do that. We're just trying to visualize what's happening. In the first reaction, magnesium's reacting with oxygen, and that's going to release a whole bunch of energy as light as it turns into magnesium oxide. So we can see that we have an actual delta H value that's written in here, but the bigger thing this wants to show you is that the amount of chemical potential energy in the magnesium oxide is lower than what was originally in the magnesium and oxygen. In the other graph, we start with water, but when we split it apart, we have to put in energy. It's an endothermic reaction. So the hydrogen and the oxygen will have more energy than the liquid water started with. So when we draw these diagrams, the x-axis is what we call the reaction coordinate. Simplicity's sake, just think of it as time. It's just time without really numbers that we've placed on it because reactions happen fast. So we see there's a straight up or a straight down. We're assuming the reaction's instantaneous in these diagrams. We'll see some later on where we don't. Our y-axis is then our potential chemical energy, our EP, which is measured in kilojoules. Note again, not every one of these diagrams has numbers on the side. That's okay. We've actually counted the numbers in here by including delta H. But we're trying to communicate, okay, where's the energy going? Is the energy going in or is the energy going out? And we can see that in terms of, are the reactants higher or are the products higher?